Okay, hello everybody. So we're going to deal with our familiar example, trying to find the minimum or the argmin of this function g, but using gradient descent this time. Okay, and so they tell us to start from 2, 2, compute one step in detail, and then explain how we would compute a second. Okay. And there shouldn't be an A, there's just one part to this. Okay. So, gradient descent begins with a guess, P, and so in this case we've chosen a specific guess, and then steps in a direction that will give, it will be in a direction that will give smaller values, that will find smaller values. Smaller than what? Well, smaller than g of p. So we just pick a random point p for a guess, and g of p won't be the minimum. So p won't be the argmin. Okay, but first we have to compute the gradient. So the gradient of g is now a map back to the input space. This is R2. And it sends xy to, okay, so I have to take the partial derivative with respect to x, single variable calculus. Here I get 8x to the third. That's 0. This will be at 2y squared minus 2x, and 0 and 0. Single variable calculus derivative now with respect to y. Okay, so here's a 0, here's a 4y to the third, here's a 4xy, a 0, a minus 2/3 y, and a 0. Okay, so that's the gradient, and so now I can plug in at my guess. Now I get 8 times 2 to the third plus 2 times 2 squared minus 2 times 2, comma, 4 times 2 to the third plus 4 times 2 times 2 minus 2/3 times 2. Okay, and what's this? This is 8 times 8, 64, plus 8 minus 4. This is 4 times 8 is 32. This is 4 times 4 is 8 minus 4/3. Okay, so this is, if this was 0, 0, we would be done. Our guess would be a critical point. And that's the point of gradient descent is to find critical points. We keep descending until the gradient is the 0 vector. Now here the gradient is clearly going to not be the 0 vector. It'll be the vector, well, let's see, 468, comma, this is going to be 40. Or did I make a mistake here? 4xy, is this right? Yeah, it looks right. Okay, so this is 40 minus 4/3. Okay, and so this is 68, comma, what is this? Maybe 39, 38.6, perhaps? Okay. So this is not 0, 0. Okay, so now we move to decrease the function value using linear approximation. So honestly, we just need to write down this one very important formula so frequently. And this time, we're going to write down the linear approximation to the original function g. Namely, g at p plus v is basically g of p. Well, plus, oh, not the derivative of g at p in the direction v. Now, because we're in the situation where the output is a real number, this derivative is a dot product. So it's actually going to be the dot product of v with the gradient of g at p. Okay, which is this vector at that point. And so now in red I'll say, we can choose which direction we step, which v. Choosing v equals negative the gradient gives a negative number, gives a negative dot product here, right? And so meaning we expect that whatever g of p was, we add a negative number to it, and we'll get a smaller value. We expect g of p plus v to be smaller. Okay, that's good, because we want to descend. We're going to use the negative gradient to descend. And so I'll even draw a picture of this now. Let's say here's our input space, R2, and we start at the point p equals 2, 2. Okay. And now, what is the gradient? Well, let's choose our formula. V equals negative the gradient at p. Well, that is negative what vector? We computed this. 68, 38.6. Okay. And so, should we step this way? I mean, let's just look at what that would be. That would be a step of negative 68, negative, so this negative number would come in and we'd hit both of these. And so it's just going to be hugely negative. This is too far, right? So linear approximation is the formula we're using. So we should only step some small amount, okay? And so I will write that. Since we're using, well, I'll just say since linear approximation only works nearby to p, we should step a shorter step. Okay, so what does that mean? In formulas, that means we don't take v to be negative the gradient. We take v to be negative, how about 1/100th the gradient? Just a very short step in the same direction as the gradient, but only 100th of its length. Okay, and so what is that? That means we're taking v to be negative 0.68 and negative 0.386. Okay, so that's our step. So I'll draw that into the picture. We're just going to step, well, first let me say that we're going to move to p plus v is then, well, p was 2, 2, and v is negative 0.68, negative 0.386. Okay, and what is that? That's 2 minus 0.68, 1.32. And 2, oops, this is a minus sign, so I need a minus there. 2 minus 0.38 is, well, roughly 1.42. Let's just ignore this 6. Okay, so this is our new point, p plus v. So I'm going to put it in my picture. 1.32 and 1.4. It's about right there. Okay, so this is p plus v, and this was our step. And we didn't step the entire gradient, that would be too far. We stepped 100th of it, and now here's our new point. Okay, so we've explicitly computed that new point, and it said compute one step in detail, and then briefly explain how you would continue a second step. So now in words, I'll say that to find our next step, compute the gradient, well, at what point? At p plus v. And then step some small amount in, say, negative the gradient, or how about negative 100th of the gradient at that point, etc. Repeat. This etc means like, okay, you see the pattern. I actually don't know what it means, but it means repeat this pattern. Okay, so I'm just gonna cross this out. Repeat this pattern. Okay, and that's how we sort of try to find, the gradient at p plus v. The gradient at p plus v will most likely be pointing in a different direction. And so then our next step will be some small amount in that direction. And so maybe I'll even add that, like grad g at p plus v is, or points in a new direction. So each step we're sort of moving around, and we'll hopefully find the minimum. Okay. Okay, so that's the whole answer. You can see the words, the pictures with labels, and also the formulas. Gradient descent uses this linear approximation formula and just takes a step in negative the gradient. Although, because linear approximation works nearby only, it should really take a very short step. And that's the idea. This will work in any dimension because we can add vectors in any dimension, and we can take the gradient in any dimension by just, with each input, take the single variable calculus derivative. And that will give us the gradient vector field.